Hello. Yes. I hope sound is okay. There is some radiator right on top of me. And I guess I
Yeah,
should
everything is
pass.
okay.
Oh, great. I couldn't hear you, but
Is it okay? Can you hear me
yeah,
now?
yeah. Now I hear you. Okay.
Okay.
Yes. Thank you for coming to the lecture. Uh, so topic for today, I will present risk bounds for regression, although I mean not so useful, but then we will apply it to SVM. So I will explain what is SVM. You probably already know it a little bit. Review the properties, why it's called like this, what are support vectors, and then I will derive a risk bound for linear classification, and we will compare this risk bound to SVM objective. And then we will see that it's kind of similar. And from the similarity, we can understand a little bit why uh, why SVM is kind of empirical risk minimizer. I mean, the SVM has a parameter C that needs to be tuned, but in practice, it's much easier to tune the C than to tune the explicit complexity. Why it's easier to tune C than other parameters that look quite natural. So yes, it's our plan.
Oh, there is some connection between bounds for linear regression and classification via SVM.
Well, yes, we are. The reason why there is a connection is because we need to introduce a margin assumption. And for this, we will need to speak about so the distance to the margin will be represented by a real number, and so it brings us. We are forced to grow through some observations regarding regression.
Okay.
So similar things will happen. So from now on in the next 4 lectures, I will speak about applications, but each time we have a risk bound, we are forced to apply margin assumption. Margin assumption, that means that, so we do binary classification still, and it means that labels of one type are in certain region, labels of another type are in another region, and there is a large space between these two regions.
And we're talking about realizable setting, right?
We will talk about both settings.
Okay, great.
So, and we just assume that we have that between these regions where we can do reasonably well, there is so in the forbidden space, like in the non-reliable realizable setting, it's allowed to have some inputs in this like margin, but the idea is that they're very rare. Okay, so let us just start. So last lecture we have a kind of like densely packed lecture, because before the break I wanted to present you two important results. First one is centralization lemma, and so the first theorem, first major result that uses this Rademacher complex. So why is Rademacher complexity so useful? And it's because of two results: centralization and contraction. And centralization means that we can estimate expected value of a function by the empirical average on a training set plus 2 times Rademacher complexity plus a small term that accounts for statistical fluctuations. So it's small because typically 1 over delta. In practice, people want to set it like 1/10 or even 1/2. And we divide this by the training size. So we get some extremely small quantity. So this is a bound that holds for all functions in our class G. But the restriction is that G has values within unit interval. So G cannot have unlimited range. Of course, there exist variants of this theorem that assume that doesn't have to be a unit interval, but when you go out, the probability of being outside this interval should go down quickly enough. But in this course, we take a very simple setting.
Could you please remind how this theorem is like interpreted in terms of machine learning? So what our class of functions G is like hypothesis class or something else?
Yeah. So when we apply it, G will be almost hypothesis class. We will have a loss function, for example, 0, 1 loss, and we apply this loss function to all functions of our hypothesis class. So that will be our G in applications. And here we will have risk, and here we will have empirical risk. I will explain loss, the more general thing like loss functions in just a second.
Okay, so now we only like derive this theorem, but not applied it yet.
Yeah.
Okay.
So contraction lemma will help us. So phi will be a loss function, and f will be our hypothesis class. And we will look at loss functions that are Lipschitz continuous. And so here we will be able, thanks to this lemma, we will be able to deal with this term. But also there was a seminar, and hopefully you spoke about neural nets. And there we also applied a contraction lemma, because we are building up a neural net is built from simpler components where we do certain linear transformations, and contraction lemma helps actually a few more complicated things. It helps when we apply activation function. So in these results, it's assumed activation function is Lipschitz with some small constant. I guess in the seminar, I just choose the constant one. Okay. So, but now let us speak about hypothesis class linear functions. So before we can do anything of this, we need like a start bound for Rademacher complexity of linear functions. And previous lecture, I spoke how we can relate growth function. So Rademacher complexity is kind of improved version of growth function. And we can apply this a certain lemma using maximal inequality. We can get some result for growth function. But here so what we get for linear spaces is some bound that depends on the input dimension, because growth functions are bounded by VC dimension, and for homogeneous linear functions, VC dimension is just input dimension. But here we will have a more ambitious goal. We want to have bounds that do not depend on input dimension. And the reason is that we want to be ready to apply our bounds together with kernel technique. So in classification, sometimes there is no embedding given in Euclidean space, or this embedding is enormous dimensions, and the dimension will be much more than the size of training set. So to still get meaningful bound, we will bound it by something else, and this will be very similar like we did for perceptron algorithm. Our bound will be some function of the ratio of input size, the norm of the inputs divided by margin size. So this is the whole plan of the lecture. Okay, I spoke a lot about philosophy. So let us talk a little bit about our first result. Let us bound Rademacher complexity of linear functions. And so here is the theorem, or maybe I should call it lemma, it's not so clear. We will bound the Rademacher complexity of regularized linear functions. That means that coefficients have bounded norm. This is very important assumption in so here we have vectors in RD. So here, in most of this lecture, X will be RD. So I will not. Is it visible? Okay, this is clear. And we will assume that the 2 norm is bounded by constant. Just these are the functions we will use. And then the Rademacher complexity. So we will take a set S equal to 1 xn. And we will have that the empirical Rademacher complexity of S of LB is bounded by 1 over B over N times the sum of the squared norms. Okay, and in this lecture, I will always use 2 norms, so I will remove them. Write it here. So by default, I use 2 norms. So here,
does the condition that we have bounded norms actually mean that it's kind of L2 regularization?
Sorry, so the question again. So
like we have the condition on our weights that the norm must be less than some number, and like from optimization we know that like this condition is equivalent to have L2 regularization on our problem.
yes.
And does it actually mean that we bound like linear classifiers but with this regularization term?
Yeah, it's indeed closely related. You're right. Okay, and I will say more generally, I will assume X is a subset. Okay, so our first little bit technical task is to prove this theorem. So if we're, like Alisher says, if we fit a coefficient W of small 2 norm, then we will have nice risk bounds. So that's a consequence. So here it's written for empirical risk. Corollary is that for the true Rademacher complexity, and so it's just expected value over S also satisfies this bound. So the bound will be B times the maximal input norm divided by N. So this thing, B over R divided by N, R is input norm, will be substituted here and will eventually appear here. Hello. Okay. So this is the plan. And so we can just in time for proof of theorem and about empirical Rademacher complexity. And so there are 2 steps. So first step, and I guess I should stand on this side so it's more clear. So I will, step A will look at N times the Rademacher complexity thing that we want. And we will say that it's smaller than B times. So first, the proof we will fix, let's look at the fixed sigma. Oh, sorry, I'm saying nonsense. We will take expected value and look at sigma 1 x1 plus sigma n xn. And we want to have the norm of this thing. we will look at this now. And B, so know that there is no square in the norm. And B, we will look at the same expectation, but with the norm squared. One x1 plus n x n square. I think it's better if you sit on this side because I will stand on this side. And the smaller is equal to sum of the norms. Okay, so these are the two claims. And now let us try to say that A and B together imply the theorem. So why is this true? Well, let's look at the square of A. Then we have almost the same thing here as we have here up to factor B. So what is missing? So here we take square of expected value. Here we have expected value of squares. So by Jensen inequality, expected value of squares is larger. So if we take when we take the square here, you get b squared times this. So we need to take square of a multiplied by big B here, and then we get precisely what we want. So here will be a b squared. Here we already have n squared, so n squared go together. So it just cancels inequality. Okay, so now our task reduces to proving A and B. So B is easier one. So sigma is Rademacher variable, and so there's just uniformly random variable in 1 minus 1 to the power n. Okay, and so this so here we have a quadratic norm. Let us look to one component of it. So we have sigma 1 x. So let's look at the j component of this vector here. This component is equal to sigma n x n j. And so we want to know what is the variance. So expected value over sigma becomes sum of variance. We can view it as sum of variances. Why? Because sigma is uniform in 1 and minus 1. So expected value of each component is 0. And hence, the variance is precisely what we need. And so here we want to have a variance of, and so x's are fixed, sigmas are random. We get a variance of some independent random variables, and so we can add up the variances of all the terms in the sum, and the term of each variance. So the variance is the variance of sigma 1 x1j. It's very easy to know because x1j is just a constant. And the variance of sigma 1, so it's just 1, because expected value is 0 and it's either 1 or minus 1. And that means that if we look at the first component, we see that so the variance of this thing that we write the details, just tell me if it's too boring. x1j squared plus xn j squared. We get this thing, and this is just for first for the j component. We need to sum over all j and all dimensions, and what we get is precisely this square. Okay, so B is proven. Now we want to prove A. So we should remember what is definition of Rademacher complexity. Empirical Rademacher. Let me make the lots of space. it's also just one paragraph, but radical complex of S, LT, which was the expected value over sigma again, and this one of supremum over W, and W is just a vector with norm at mode B of W times x1 sigma 1 plus W xn sigma n. Okay. And now it should be easy. So let us fix some notation. Let us first get rid of the supremum and fix a notation and define W sigma to be the W that maximizes the sum. Okay, how can we bound this? So by Cauchy-Schwarz, right? It would be very natural because we have a bound on W and we are interested and here we have a norm. Okay, and it's already proved. So we apply Cauchy-Schwarz. So let's look just at this vector. This vector is bound. We see it as a dot product of W sigma and the vector x1 sigma 1 plus xn sigma n. Sorry, it's exactly equal. And now we apply Cauchy-Schwarz. So we say norm of W sigma times norm of this vector. And we are already done. It's very nice proof. So A and B are both very nice easy steps. But we have proven something we will use all the time, which is this thing. Rademacher complexity of linear spaces is equal to B times maximal norm of an input divided by n. By square root n. So let me write this corollary. So I can write it here, since we will use it later. So Rademacher complexity of LB. So and here the true Rademacher complexity. So when we average over this, is bounded by B times R over square root n. Where x is equal to all inputs with norm at most r. Just bulk radius r in the center. So that's our corollary. So note that here we have square root r n now. So this is important observation. Rademacher complexity goes down by square root n in the data. And this is not surprising because our risk bounds for VC dimensions also have been agnostic. So this all this theory is for agnostic setting. And so this behavior this going down with 1 over square root n is very tight. So there is a whole business of making risk bounds that go down with 1 over n. I will not talk about this business because it's more complicated. It's just introductory courses. Already enough things we have. But then you need like stronger assumptions. So you need to have stronger assumptions on input distribution. And usually it's for specific learning algorithms. Okay.
What is the intuition behind behind the fact that Rademacher complexity and we see dimension goes down by when n tends to infinity. It's like when we have a lot of samples, then it's easier to generalize, right?
Yeah. So of course, yeah. That's the intuition. It should go down. The more samples you have, the better you can estimate. The more confidence you can have on the on your estimate when it has to apply to a large set of functions simultaneously.
Okay, thanks.
Yeah. Okay. So that's the technical part. And then I wrote in the notes a lot of explanations, but they're kind of like repetitive and simple. So let us now consider a simple regression task. I will first clean up the board here. Okay, so when we speak about regression task, we get in general we need a loss function. So we will have a loss function L, and it takes an estimate. Well, basically, we have sample space. We have so now y might be equal to r, and the loss function compares two labels: a predicted label and the true label, or I mean the label given in the training set, or test point or whatever. Okay, and most popular is quadratic loss, y hat equal to y minus. But okay, let's now take. Oh yeah, okay. Then the risk will be defined using the loss function f. So it is just expected value over x for p. Sorry, the pair xy over p, because we are in an agnostic setting. Y minus the loss of. And so we will fix in each result the loss function. And this is the definition of risk. Completely natural, right? Why do we keep x? Sorry, f of x. Because so we take pairs xy over our measure p and put output pairs, and then we give it the true label and estimated label. Oh, by the way, I'm using, not writing it well, so I use the first document for estimate y hat and the second for the true. So here I will say f of x, and here y. And so we take the pair xy according to p. Okay, let me write it a bit more clear. So pair xy is taken to p is measured over. So when we apply this result, z will be input output pairs.
So this definition is like universal for realizable and agnostic settings.
Yeah. In all books, there is this convention that risk with loss function is defined by this most natural way. I'm not sure what is problem But if there is problem, we
Okay, I think I just.
Yeah. Okay, and then empirical risk is defined in very similar way. So again, so here we have S is a list of input output pairs. X n y n. Just 1 over n. Sum over all items in the list. L of f of x and y. So if we have training set, then we look at the loss function. Or can write it more concise, but I don't need to say what is S. All not important. What counts is that we understand what is what. And so let us now give like a very simple risk bound. We get almost directly from these 3 results. So here for all of these, so with x is equal to just a ball of size r. So Euclidean space for proportional to n. So 1 minus delta for all f and LB. So LB, I erased the definition, but I guess you remember it, right? We have the risk bound smaller than empirical risk. Oh, I didn't say which loss function I'm using. So I can write this here, where y at y is equal to minimum of an artificial loss function just to get a simple result, y minus y hat. Okay, so I actually the absolute value norm is not artificial, but I clipped it to 1 artificially just to get rid of some annoying thing. And so here is the risk bound RS, oh sorry, RC. Okay, hope it's still readable. Let me make it a bit nice. RC plus the level 2R by square root n, and then the fluctuation term. And 1 over delta over 2 Okay, so now this corollary, it's almost directly follows from these 3 results. So is it clear? Okay, so let me write a bit more. So we will set what will be G. G will be equal to loss function applied to each function in LB. So let me just for clarity, because I know that many students complain about this. So what does it mean? So this is the set of all pairs XY that are mapped to loss of f of x y for F in LP. Okay. So note that our function is one Lipschitz because we just take absolute value function, and adding constant is one Lipschitz. Well, not constant, but okay. Subtract a linear function with coefficients at most. So one Lipschitz. And so we can apply contraction lemma. That means Rademacher complexity of G is the same as LP.
Why
Yeah.
do we, the contradiction, why do we need that phi is from R times Z?
Well, look here.
Okay,
We have so Z is this pair of inputs, and we use the inputs, but also the value of the function.
The value of function is
Yeah,
whole number.
yeah,
But yeah, okay.
yeah. And so when I apply this after it, it means I use both arguments of functions in F and values of these functions in F on these arguments. This is what's happening here. And so
Isn't y so y is x and y are vectors, no?
X is vector, Y, yeah, okay, it's just a real number.
No, I mean x and y are not numbers, they're vectors.
So yeah, X is vector in this example. But for this result, it is all valid for any X, and then for any set Z. Yeah, so here in the seminar, you should have proved contraction lemma, but we didn't use the arguments here. But the proof doesn't change if there are arguments. So I just told like prove it without these extra arguments, because otherwise you have to plug them in everywhere. It's nasty. Okay. So we know what is G. And now let us check that this G satisfies all the conditions here. First, the G should have values in 0 and 1. And this is clear because minimum of 1 and something positive, non-negative, it's okay. Over Z is delta, and then with probability 1 minus. Okay, that's all the conditions. So we can directly apply this risk bound here. And we already said that Rn we can replace by RLP because it's one Lipschitz. And so we get this result. So what do we have? RG, RNG. Oh, I forgot the little ends here. RNG. G is equal to L after F. L after LB. And so this is 1 times Rademacher complexity of LB. And here is formula for Rademacher complexity of LB. And we have the same X here. That's the corollary.
Okay.
Okay. So next question. Okay, you can complain now that this is a quadratic loss now. What risk bound do we have? So I will just make the changes and erase this to save a bit of time. So now we have a little bit bigger bound. 4 R squared B squared. So loss function will be y minus yx squared. Okay. I was a bit silly in the notes. I should put like 1/2 because it's standard thing to do, but I forgot it. So it's not a big deal, just 1/2 and over square root n. Right here. Square root n 2 plus Now I'm one over done. Okay, it's a whole mess, but we run. Now the lecture goes very slow because I cannot write. That's all. Okay, actually here we can divide by 1 over square root 2. I was a bit lazy. But it's not important, so it's a little bit better. Okay, now we want to prove this corollary, and it's the same proof, same structure, but we need to we have a little bit of trouble. Okay, so what is y in this case? So we are applying inputs with norm at most r to coefficients with norm at most w. LB here, norm at most W. So we can take y in the range minus RB, again by Cauchy squared. So this is our y. And now we are a little bit in trouble. We want to do the same thing. Set this equal to this thing. But here our functions are not in value 0, 1.
Yeah, but you can divide.
Yeah, exactly. That's the only thing we need to do. So we divide these functions by 2RB. And then at the end, we apply multiply the risk bound by 2RB. So we scale the loss function. So these two scale linearly. So we scale them down, get the risk bound, and scale them up.
Wait, so you say if we divide all the functions by 2RB,
Yeah.
our loss functions will also divide by 2RB.
Yeah.
But wouldn't they divide by 2RB squared? Because our loss function.
Yes, sorry. Good point. Yeah, I mean, we divide by 2RB squared. Yes. Okay, and this is why we have here 2RB squared. So the same thing. But we have additional factor 2. And do you know where it appears?
Maybe because we when we divide by 2RB, we can get negative results.
Oh, wait, with this 2.
No, it's not because,
But also we need additional 2 because of Lipschitz function. So I should double check this proof that I didn't forget it. Additional factor 2. Okay. Yeah.
Could you please explain once again? So we are scaling our functions from G, and then we get that our loss function is also scaled, but we need to somehow turn back to initial loss function. So don't we need to scale back? So
okay, let me do the scaling. What we get here is 4R squared B squared is smaller than. No, we don't have this factor here. We have 1. And here we have again 1 over 4R squared B squared. Okay, you understand what I mean, right? So this is just this equation. And I now realize that here I should have actually factor 4. And this has to do, there is an additional factor 2 when we apply contraction lemma. And we got the quadratic function. And the values goes from -1 to +1. But the derivative has additional factor 2. So we only have that our functions are 2 Lipschitz.
okay, so the matter complexity is 2 over square root of x.
Yeah.
But the additional
No. Oh, wait. Yeah. So So LB didn't change. We changed the loss function. And so there is more text missing. So there should be a BR here. Should be. Yes, because
we divide all of our function.
yeah, of course, yeah. And so the function becomes Lipschitz. Yeah, so the Lipschitz coefficient is. Okay, clearly I messed something up in this proof. Okay, so what is Lipschitz coefficient? It is 1 over 4 r squared b squared. And we get the value, because the derivative is twice the value, there is additional times 2. So for any quadratic function, we have the promise that derivative is at most twice the value of the function. I mean, when argument is at most 1, but argument is not. Okay, I should write it carefully. Okay, let's say it's exercise. It's just some calculation. You understand all the steps. And now, okay, if I do it step by step, I cannot speak about, I only have half an hour and I want to speak about SVM now. Okay, so I will delete this and then you can scrape your memory. Try to remember from machine learning course what you know about SVM. Yeah, so probably what I wrote in the notes is just correct about this issue because I carefully wrote it. I didn't understand why I had to do it, but okay, now I understand a little bit why I should write it careful. So students ask me like, no, always the same thing. And then they force me to write it. Okay, so let's go. So SVM. So what will I do now? I will remind you what is hard margin and soft margin objective. I mean, it's easy thing. And then I will explain the name, what is support vector, how we can easily understand that there exists such points. There exists, how it's called again, representer theorem. It's something very simple. And it's tradition that the teacher in statistical learning theory needs to mention about this, but it's also useful because it helps you to understand why kernel SVM can be implemented easily. And then I will derive margin risk bound. Is actually very important topic. What is margin risk? What is a margin risk bound? It's just a risk bound that uses empirical margin risk. And the bound is only meaningful if you have a margin assumption. And then finally, I will compare the margin risk bound to the SVM objective and explain why, or like somehow argue why tuning this C parameter in SVM algorithm is easy. Okay, so know that when we computed sample complexity, so imagine we need to classify cross versus bar, and we want to minimize sample complexity. Then it was our plan was to choose either the maximal. And so let's speak about threshold classification, and we put either the threshold at the bar or at the cross. It was our best way, our strategy to get the best bound. When we put it in the middle, it was a little bit worse, the bound, if you were to work it out. But under margin assumption, it's actually better to put it in the middle we had some simple exercises when I started to speak, some simple observations when I speak about perceptron algorithm. And this is what SVM is doing, but also in the plane. So it searches. Well, let's do a simple example. So it will, if we have a few points here, then it will search for hyperplane. In this case, just a line that maximizes this distance. So, so for each point, we can calculate the distance to the separating to this line and maximize it. And this is called hard margin objective, when we assume that there is a line that does separate it and we maximize the distance. And so from mistake bound of perceptron, we already know how we can express margin. It is just the minimum of x1 times w divided by norm of w. Oh, and we have to multiply by the data. And then the same y and x and this method, two questions before you want to implement it. First, is this W unique up to scaling? And second is how can you find the W? It's kind of two natural questions. So let's try to answer them. Okay, I will first answer how to find W. We can reduce it to convex quadratic programming problem. And then you can apply gradient descent, and there exist specialized methods for this specific problem. So how do we reduce to quadratic programming? Well, we will put 1 over W. Can we put in the front? Okay. And now we can choose a scaling so that this minimum is equal to 1. And so 1 over W was here, and I put it in the front, nothing happens. So this is our objective. And so we can always choose scale of W such that the minimum is 1. And then we have this objective function. So we want to minimize. Sorry, we want to maximize. Yeah. So we want to maximize the margin. I write minimize. Yeah, I was extremely tired this morning. It's okay, I always make such mistakes. But now the max is outside. Yeah, that was. No, the margin is the minimum. I mean, maximize over W. And so, yeah, and W can go here. Okay. And so now when we require the minimum to be 1, then the problem is maximize 1 over W such that y1 x1 times W is at least 1. Y and x and W is at least 1. Okay, and now we have convex program, and now we have convex optimization problem, because 1 over W is convex function. Is it? Okay, let's do one more step. Instead of maximize 1 over W, let's minimize W squared. And then we are at hard margin SVM. Minus W squared. And this is convex function. So moreover, it's strictly convex function. Okay, so these problems, they are equivalent. So assuming that
How did we arrive with the conditions like?
yeah, so we said that this minimum is equal to 1. Okay, and minimum being equal to 1 is equivalent to this thing. But here we have inequalities. But note that when all inequalities are strict, it means that we can make W bigger, smaller, I mean. So we can make W smaller, and hence we are minimizing further. So in the optimal point, minimum, this minimum being equal to 1 is the same as this thing.
Okay.
Yeah, it's something like in every machine learning course, they explain this. So, and since I'm normal, I also explained it. Yes. Okay, and now we can understand about uniqueness, because this is not only convex, it's strictly convex. And another way to understand it, imagine that there are two optimal points, W1, okay, W and W tilde. So imagine that they both have the same value here. Then the point in the middle will also satisfy all inequalities. So we look at 1/2 of W plus W tilde. It satisfies these inequalities, but the norm will be smaller because constant W being constant is a ball, and you go in the inside of the ball. Okay, so it's very clear that W is unique. And okay, since convex problem, we know how to solve it. Okay, these two questions are done. Let me check what I also should say. Okay. Now, finally, representative theorem. So representative theorem, so now we have unique solution. And representative theorem says that this optimal solution, W star, is always of the form beta 1 x1 plus beta n xn. So here, I say that the beta i's, they are just in R. In fact, we know something more from KKT condition, that the betas are non-negative. But okay, we don't need these advanced things now. Actually, in lecture about neural nets, we will speak about KKT conditions. But for now, let's not speak about it. Okay, why do we know that just real numbers BI exist such that this is true? This is by orthogonal decomposition theorem. So what we are saying is that the optimal W lies in the span of the axis. But imagine that we take some W tilde that's not in the span. So W tilde is not in the span of axis. So then this W tilde can be written, decomposed as W orthogonal plus W parallel. Okay. And so now let us think about this norm. This norm will be equal to W orthogonal plus W parallel, so Pythagoras theorem. But W orthogonal doesn't change anything about this. So we can drop W orthogonal and objective decreases. So that's it. Representative theorem is proven. I'm not gonna write a formal statement, just check the notes. There should be homework exercise about a simple homework exercise, but it's also easy. Let's not waste time in it.
So basically that's an explanation about like the name, why it is called support vector machine.
Yes, because the solution is supported on some vectors. And we also proved that if X live in low dimensional space, in one of the seminars, there was an exercise to prove that the number of support vectors you need at most number of dimensions. So with this what Karateodori theorem, it's a consequence of it. It's kind of like a favorite seminar exercise. But I think you didn't get there because it was slow in the list. But you can check it when it was about leave one out, risk bound for SVM. It must have been in one of the first seminars. Okay. Yes. So this about hard margin SVM. Now let's say what is soft margin SVM. Okay. Let us go to our first example. And just let's think that we get a point here. So just think about mouses that die when you give certain level of poison. You want to know which level is enough. And you get something like this. And then this mouse might not be, might be exceptional mouse. So maybe the guys you hired to kill mouses did everything right with this mouse, but just outlier mouse. So you should not be angry to your killers. Yeah. Vendor fence or whatever, they did everything right. Okay. Yes. So that means we should just drop this one, ignore this one somehow, and still think when we choose the margin to put it here in the middle. Okay, and so how do we get this? Well, we change the objective. So we look to this minimum plus sum of hinge losses of points. So what is it? Okay, let me write the simple objective again. We want to minimize over W the max of the same thing before. Let me write it short, but yi times W divided by W I smaller than n plus okay, plus the hinge losses. So we will have, there are two objectives, we balance them with some sum, and then we have yi xi times W minus 1. Sorry, and I can draw. So this maximum will be 1. Let me write it again. Minimize 1 over. Okay, we will just adapt this thing here. So we want to minimize W squared, the same thing here, but we correct with sum over yi W times x minus 1 minus this thing. Okay, and so the loss function that given y hat is equal to 1 minus y hat y. It's called hinge loss. Okay, and now there are some remarks about it. Okay, so remarks. So if we take C very large, then we have the same as realizable set. Because C very large means that all these inequalities need to be almost perfectly satisfied. And then we minimize W. Okay. Another interesting thing is that we had the risk bound for perceptron algorithm and agnostic setting. And so let's compare these risk bounds. It's R squared times B squared plus 2 times sun max of 0, 1 minus y x times. Oh, I forgot the maximum in our objective function. So it is if you have maximum 0, 1 minus yi xi w. So we have almost the same thing here. We just have to set c equal to 2 over r squared, and we have the same objective as the mystic bound for agnostic setting. Just kind of striking. And which is only known like 15 years ago or something. Even though SVM was popular for 8 years, it was the best algorithm at that point. Okay. Yes, what else should I say? Okay, so then there is uniqueness is now proven in the same way. So you can transform it. So you can set these maximums equal to some slack variable. And then reformulate it to a similar problem. And it will become a quadratic programming problem, again, in a convex set. So now we will have, let me write it. It's in all machine learning courses. So we have maximize W. So maximize plus C times psi1 plus psi n. I'm trying to save a bit of time. Such that yi xi times w is bigger than 1 minus psi I. So for all I, still n. So that's equivalent. So now we have more variables, the variables in w and xi's, but again, it is the constraints are linear, and objective function is convex, not strictly convex. So you need to be a little bit harder that if there are two solutions, it's just a small calculation. If you have two solutions and the average of two solutions is again a solution that that has smaller objective. Okay, but that's enough blah blah. So let's now go and speak a little bit about margin risk bound. So note that in applications, I already said that in applications, input dimension is huge. We want a risk bound that does not depend on input dimension. And these theorems will help us to obtain it. So if we would use VC dimension, then our risk bound would be something like, so the excess risk, which is an agnostic setting, is the risk of our classifier minus the best classifier. And this would be proportional to square root of input dimension divided by training size of training set. And so we will achieve something better. We will have something proportional to max input norm divided by margin size, and then 1 over size of training set. Okay, so this is our plan, but to obtain this, we need to introduce margin risk. So I will use a special loss function. So let me compare. Maybe I should keep the objective function. So what are our loss functions? So here we have loss, and here we have y times y head. 0, 1 loss means that here we are at 1, then we go to 0. 0, 1 loss. Then margin loss. What is the whole reason why we need margin loss? We want to apply contraction lemma when we apply the loss function, but we need 1 Lipschitz, and 0, 1 loss is not 1 Lipschitz. We cannot apply anything like this. And this will be solved by using an upper bound on the loss, which is margin loss. It has a parameter rho, and it looks like this. So margin loss. So we have phi rho of y hat y equal to, and then there are 3 regimes. Okay, I will not write it. And then there is hinge loss eventually. And this goes like this. Except we have to set rho equal to 1. So the hinge loss it's like this. Okay, but now we will focus on margin loss and then apply the same theorem we had before with the same proof. So and we get a nice proposition. So we get a risk bound Rp of f. So again, we have that for all f in we write it a bit lower. The full detail of the theorem I will write in a second. Just so now we consider functions f. So f is a set of functions that map to real values. And then we say that for all f and f, we have the following bound. The true risk of the sign of f. So we will use the sign of such classifiers to make binary predictions. And this will be bounded by empirical risk on a given training set, but empirical margin risk on a given training set V of f plus 2 over rho. So rho will be a parameter that we will need to optimize the Rademacher complexity over class of functions, and then plus the fluctuation term. So it is 1 over 2n times ln 1 over that. So this is okay, and we have the same thing again. So P as a measure over x times y. So y is now of size 2. And now I should say what is empirical margin risk, but it's clear. It's just empirical risk when the loss function is margin risk. The loss function is this black dotted line here. So note that this empirical risk, R hat, is an upper estimate, is upper bound of empirical risk. So here I speak about empirical risk of sign of after F. Okay, it's a bit messy. So F is a function from here with real values. So we need to transform it to a classifier. And empirical margin risk is upper bound on this classifier. Okay, so this is the risk bound we get. So why do we speak about it? From SVM, we get actually a vector W, which gives us a function from vectors to real numbers. Therefore, we have to apply the sign. Okay, and so how is this proven? This is again, this and this applied together. But now we need to, this and this applied together. Why? Because margin loss is a number between 1 and 0. So we can directly apply this theorem. And it's also 1 over rho Lipschitz. That's why we get not 2, but 2 over rho. So now there are 2 remarks. So we will run our learning algorithm and then apply rho that suits us. We will do kind of optimization. So note that here is a bias complexity trade-off. So what happens if we choose rho small? Then this term will become small. But this term will become big because many points, if a point is correctly classified here, it's on the right side. So y times y hat is positive. But when we choose rho too big, it will be penalized almost as much as a wrongly classified point. So if we choose rho very big, this will go to 1. And so we have a bias complexity trade-off. Small margin corresponds to high complexity, a high regularization term, but usually a small, likely a smaller empirical margin risk. And so such bounds are meaningful when you manage to find a reasonably big rho for which empirical margin risk is small. And so recall empirical margin risk is upper bound on margin risk, on true risk. Okay, and so there is 1 task left, but it's now 4. So I will, but it's not so much. So let's compare this bound with SVM objective, and then lecture is finished. Okay, so so let us work a bit harder on this bound. So F will be a set of linear classifiers, so it will be LB. And so here we should fill in this bound here, BR over square root N. So BR over square root N. But the question is, how can we choose BR and square root N? And here, my aim is to get H loss here for this term. But note we have a parameter rho here. So how can we get, how should we choose rho to get H loss? And our plan is as follows. So note that if we scale F here, then nothing changes in the thing we want to bound. So we are free to chase speed. And so our plan is to scale F with 1 over rho. And then we get the H loss here. Okay, so we scale F, and then in this definition, so let me write this definition so that it will be even more clear. So what is it? It's equal to 0 if y hat is at least 0. It's equal to 1 if y hat is no, that's not one. It's equal to 0 if y hat is bigger than 1. is equal to 1 if y hat is smaller than 0. And otherwise, it's linear function. So the value will be 1 minus y hat divided by rho. So that this line, so when y times y hat is equal to rho, it drops to 0. Okay. So when we apply this function to SVM, what do we get? So here we get the sign of W. Let me write it as real mathematician. RP x goes to W times x. Sorry, xy goes to W times x. No, that's it. So here we have the same f. I will not write it. Sorry, what did I want to say? I want to say that if I multiply by rho here, then when I apply the margin risk inside here, it will cancel. So y hat will be multiplied by rho, and here it will be divided by rho. And so these two rows cancel, and we get the hinge loss. Margin loss will be equal to hinge loss inside this interval. But it will be larger when we go to the left. Hinge loss will be larger for this choice of row. And this is our plan. Okay, I will go quickly about it because it's the last, then we can finish the lecture. So this means that when we apply our function, so we will, so the first step, let's divide here by the norm of W. So here scaling doesn't affect anything, and set rho equal to 1 over W. That will be our choice. So we set rho equal to the scale here, what I just explained. And the result is that here all these functions, the coefficients have norm 1. So when we plug in here Rademacher complexity of LB, we can set B equal to 1.
Excuse me,
yeah.
Is that true that margin must not depend on our set of classifiers? So it must be some number, but here it like depends on W. It is not a problem?
Okay. So it's not a problem because the risk bound holds for all classifiers in our set. But you're right. Now the set, the B we choose depends on the classifier. We can get rid of this by making a version of the proposition that holds for all values of B. And it's explained in the notes how to do it, and it's actually homework task. Well, I didn't make the seminar yet, but last year it was homework task. So it will be either in the seminar or in the lecture. So how to deal with these B's, and actually also how to deal with the rows. Okay. So we said B equal to 1, and then what is the risk bound we get? So we get the hinge loss. So now let us apply this to the W we get from SVM algorithm. And so our risk bound will be, so our P of x goes to sine of W times x. So W star is solution of SVM. No, it will be bounded by the hinge loss, which is this thing. Okay, I will just write hinge loss of W star. And then the second term So know that rho was chosen 1 over W. So we will have R divided by square root N times W. So what we see is that we don't get the SVM objective because it has W squared here, and we only have W here. So it's a little bit different. But on the other hand, it's very similar because the hinge loss is equal to this thing. So SVM is not really empirical risk optimizer in the sense that it optimizes a risk bound. But on the other hand, so when you run SVM, but on the other hand, we can understand that SVM algorithm takes into account some regularization already implicitly, which is closely related to the risk bound. And if you would run SVM, like select imagine that we look to if we fix the norm and we look to the best classifier, we would see something quite bumpy, and then suddenly it will go down a little bit. But in SVM we do cross-validation on C, and there we see something like it goes down smoothly, like in little steps, and then it goes up again, but only in very smooth steps. And so in practice, it's much easier to tune C than to tune W. Like accuracy on test set is much smoother in C. And this is because SVM algorithm already takes some approximation of risk bound into account. So if there is a sudden drop, then the sudden drop gets kind of smeared out in a big range of C. And so it's much easier to train C. And in practice, you need to tune many parameters, but there can be parameters in feature extraction, the construction of kernel you're using. And if they're all kind of like close to convex, it's easy to tune them. You just do them in turn or in whatever method you want. But if they're all like full of local maxima, like if you tune W directly, there's all these local maxima. Well, no, I mean, if W get, by the way, I did it opposite. So W is small. If the curve is difficult, then of course you get trouble in optimizing it. Okay, I've been talking long enough, so let's go to the quiz. So I will end.